So in Switzerland now, yeah, I'm going to use the class to use. In Switzerland now, those are actually classified as weapons, and you're supposed to give them to the Kantonspolizei.
Oh yeah, I
The
think
higher,
those.
yeah, the higher up ones.
Oh, anyway, I
Where'd,
gotta run this
where'd
slides.
you go?
Good morning. Ah, okay. Hello. Good morning. Thanks for being here so early. This is Passover Network and Research Group. I hope we are in the right room, everyone. Brian just declared because we are here, it's the right room.
It's the right room.
So, this is IETF Note Well. If you would like to read it, you can download the slides and enjoy it. And just reminding you that it's here and also that we are supposed to be nice to each other. What we're all trying to do, I'm sure. Housekeeping. Uh, it's not a big room, but still the chairs would appreciate if in-person people would still join the Meeteco queue if you like to ask questions, because it's much easier for chairs to track the queue and find out who was there first. And after you ask your question, you can also leave the queue. Meeteco participants, yeah, please mute until you're actually actively speaking, which means you join the queue as the first or you are presenting. Remote speakers can probably present themselves or just ask me and I'll run your slides. We have a minute taker, I guess. Thanks, Xing, but Xing is remote, so if anyone in the room would like to assist, because I guess it might be beneficial if someone in the room also helps with meeting minutes. Any volunteers? It's the worst part of every session. Oh, come on.
Next person to make eye contact with the chairs.
Yeah, we have plenty of time today, actually. We can wait.
I see Anna thinking about it.
It's
Oh,
okay.
you should. You should. It's great.
You
It's
have
a great way to understand what's going on. You have a backup.
Yeah, you have a backup, so it's easier. You're not alone today. And actually, we have recording.
Yes.
So if you are not sure, you can always. I'm not going to upload minutes immediately after the session. You'll have a few days. So thank you very much, Anna.
So hop into HedgeDoc and
Yeah, you can collaborate, yeah,
yes,
with
put it in
people.
HedgeDoc. Yes.
Oh, yeah.
Go ahead. Oh, am I the first one up?
Go,
Yeah.
go help Anna.
Yeah.
So yeah, thank you very much. Yeah, we are supposed to wear a mask. I'll get my one on as soon as I finish with coffee. You don't want me not caffeinated enough. Agenda. We actually do not have a really full agenda today, so we have plenty of time for discussion for everything. So Brian will start today with giving you an update on Cyan, and then we have a presentation about IPv6. Wow. And it's not my fault this time, actually. And then we have a number of Alto presentations with guest speakers. So any last minute agenda, Bashan? Anyone has a great idea they want to share with us this morning? Okay, good. So not much happened, to be honest. Past properties draft is now with Colin for IRSG review. Hopefully we'll get it published soon. So if you have any great drafts this research group shall adopt, please send them to the list. And with this, I guess Brian will start presenting as soon as he finishes with helping Anna. I am going to share the slides.
Yeah, so hi Corinne, hi Nicola. I shamelessly stole your slides because I wanted to give everybody an update from the chair for things that you may have missed at the interims. We had a couple of very productive but not extremely heavily attended interim meetings, so we did want to report out kind of what had happened there. How we got to where we are with Scion was back at IETF 113 in Vienna. There was a side meeting about Scion and then a presentation at Routing Area Open. And the feedback that came from that is like, neat, that's an architecture. We don't do architectures. So we decided to pull into PANRG the work of thinking about how to turn this into things that can be worked on more or less independently within the IETF. So there are 3 drafts that were like basis for this discussion in PANRG. One is the overview draft. One is the component analysis. So I think it was the first interim meeting that we had where the feedback from that meeting was actually, can you look at how we can take the system and break it up into components and figure out sort of what the interfaces are between those as input to the decision to, figure out how to document those components. We were happy to accept that the work of having that discussion within PANRG. The rest of these slide decks here are, or the rest of these slides here are largely an overview of what's going on in Scion. Have a look at the overview analysis draft for that. The interesting slide is here. So the incorporation of that feedback about doing component analysis, 3 components pretty quickly fell out of that discussion. And these are, I don't want to use the L word, but these are almost layered on top of each other. So there's the control plane PKI, the control plane, and then the data plane. Some of these are closer to things that could be standardized. Some of these, they're open research questions. Some of these are kind of maybe the Scion way of doing things and maybe less interesting on their own within the IETF. But the feedback from that was to essentially take what's been written about Scion to date, right? Like, so the source data or the source content for the specifications, actually bring those into internet drafts with the intent of publishing them on the independent submission stream as sort of like, ETH's implementation of Scion. Or the Scion Lab implementation of Scion. It's a very common thing when work comes into the IETF, we don't really know what to do with the source work comes in as an ISE RFC is sort of like here's the starting point, and from there we'll go on that. So the Scion folks, if you have questions or anything to talk to them, they're over here, Corinne and Nicola. We'll be doing that over the winter, I guess we could say. PANRG will remain a discussion forum for things about Scion until we look at those documents and figure out, oh, yeah, this actually needs to go into this area open meeting for a possible BOF, or this needs to be brought into this working group, or this needs to be wholesale replaced with this thing that already exists in the IETF and can be very easily adapted to work with Scion, et cetera, et cetera. So in the meantime, questions, comments, et cetera about Scion, we're happy to have those discussions on the PANRG list. I think we're not planning another interim because like you guys just have some work to do before you can come back. And we expect to have sort of a report out on that and possibly a discussion about next steps in research. My personal, like, chair hat off, my personal bias on this is I think there's lots of really interesting stuff to be done in the path discovery and dissemination space. But we'll have that discussion in Yokohama. So if anyone has questions about what's going on in Scion, those really wouldn't be for me. This is just, catching people up who weren't in the interims on what's happened. I guess we can take those and put Nicola and Corinne on the spot. Otherwise, we can move on to the next presentation. Going once, going twice. Thank you very much.
Okay.
So good morning. I'm Maxime Pirot from the IETF Louvain. So I'm going to present something that was really collaborative work within the lab. So I'm a PhD researcher. My advisor is Olivier Bonaventure, and with all the team and also colleagues from the IETF Louvain. So we've been reconsidering what IPv6 can do, what the roles it can play. Next slide, please. So our kind of thought experiment started looking at how IP addresses are used today. And so we've been looking obviously at IPv4, and in IPv4, one address usually identify a network interface. And so a host that would have multiple network interface as one IPv4 per network interface. But not much more than that due to several reasons. The Linux kernel is not really great at handling multiple IPv4 on an interface. That's one reason. The second reason is also that we've been accustomed to the limited IPv4 address space, and this is a big constraint. So when IPv6 came in, it obviously alleviated this constraint space problem by bringing many more address. But the stance, so this is a position paper. It's an editorial paper published at CCR, and we tried looking beyond that. So, okay, we have now many more addresses, but does those addresses brings more possibilities for endos or in the network? And so we essentially try to look, okay, can we do better than one IP means one interface? And one of the findings that goes hands in hand with one of the strengths of the lab is that obviously multipath transport protocol really help in that endeavor. So next slide, please. So you're probably wondering, what are those roles? And if you have a quick glance at the paper, you probably see a beast like that. And you're like, okay, so what are those roles? This is a nice meme courtesy of one of my colleagues, Louis, that I took for the slides. Next slide. So actually, we looked at many aspects that can be improved thanks to IPv6 addresses. So we looked at privacy, load balancing, segment routing, differentiated services or differentiated routing on multicast. Next slide. So I will start by addressing the elephant in the slide, let's call it. Let's talk about multi-homing. So in IPv4, when an AS is multi-ohm, so here it's AS1 that has two provider, AS2, AS3. What is usually done is that AS1 is first, it's an AS, so it requests an AS number and it will announce its prefix. It has one prefix that is announced over the two links, and there are many tools and many tricks in BGP to do that and to be flexible. And this is a whole domain in its own that I'm not that much knowledgeable of. But we've been looking at what's the effect of this. So the effect is that actually a lot of the ASs are stub ASs. So they don't have clients. They're just reaching the internet through one of several providers. And when you look at the quantity of BGP message that travel over the internet, you can see that roughly half of them, their messages coming from stubs. So stubs are really putting a strain on BGP in the internet. And we've been looking at this proportion for the last 10 years, I think. This is data from the paper, and it's roughly constant. And it's roughly also constant between IPv4 and IPv6. So they're likely used the same way, actually. Next slide. So obviously, the IETF is aware of this problem. And this is one of the latest attempts that I know of, obviously. Next slide. So in IPv6, the proposed solution is a bit different. So the first striking difference from IPv4 is that the bottom network is no longer an AS. So here we call it enterprise because it could be an enterprise that is interested into being multi-home for resiliency and that kind of stuff. So here it's no longer an AS. What this enterprise do is that what this enterprise does is that it receives provider aggregatable prefixes from each of its providers. So it will receive a blue prefix coming from AS2, and it will receive a yellow greenish prefix from AS3. And with those two prefixes, it will distribute them inside the network. And each of the device, here we have a smartphone, will receive one IP from each of the prefix. The really advantage of this solution is that it doesn't require BGP. So BGP is less used for solving this problem. But it has also a really cool feature is that the device can choose which address to use. Next slide. And so when the device has multipath transport protocol and those two addresses, then it can really do cool stuff, such as quickly reacting to a provider failure because it's monitoring how the connection is going through one provider and could migrate the connection to the other provider. It could also dynamically choose the best provider, and the best provider could be defined by the application. One application needing high bandwidth would choose, could migrate from one provider to the other, hoping that there is more bandwidth on the other, or could migrate to a lower latency provider if lower latency is required. But there's many combinations that we can do also. We can use the two providers together redundantly, using FEC, using, I don't know, plain redundancy, or in an aggregated fashion. Next slide, please. So to benefit from that, I thought it might be good to look at the status of multipath transport protocols within the IETF. So there are a bunch of multipath transport protocols with a different set of features. Most of them are overlapping, but all have their particularities. So the first I thought of is SCTP, for which the work is still ongoing through this draft. And SCTP today is deployed mostly for WebRTC. So the second multipath transport protocol is MPTCP, which has a new RFC for its version 1. And today MPTCP is largely deployed in the sense that it's available on mainline Linux 5.6, and it's apparently available in many Apple devices as well. Going further into the timeline, or closer to us rather in the timeline, looking at QUIC. So QUIC, I put it in the multipath transport protocol because it has a feature or two that relates to multipath transport protocol. But it has also a constraint, is that you can only use actively one path at a time. But QUIC has large-scale deployment today. And the following work in that direction is multipath QUIC, which is still an ongoing effort, and enable the use of several network paths. Next slide. So we've been involved in QUIC for some years, and we've been looking at how QUIC can be used on multi-home servers. So we've been looking at multi-home client in the example, but it could also be multi-home server that will also would like to be connected to several providers for failure, resiliency, or for redundancy, and all those purposes. So when looking at QUIC, there is a bunch of features that are useful. So QUIC enables the client to change local addresses. This is called connection migration in RFC 9000. The server have a mechanism to defer client to another address just after the handshake, and that's called server prefer address. And then there is this ongoing multipath QUIC that would enable the use of several network paths. But there is a hole in all that, is that QUIC v1 lacks a way for a server to announce or to advertise additional addresses that relate to the connection. Next slide, please. And so we've proposed a small extension to that. I'm not going to discuss in detail what it's about, but if you're interested to use QUIC on multi-home servers, this is something that would likely interest you. Next slide, please. Okay, so let's look now at the other animals. I would take some of them. There's more in the paper. But let's look at privacy, load balancing and segment routing and try to reconsider how IPv6 addresses can help those areas. Next slide, please. So on the clients, there is also something that is well known, RFC 8981, so which defines temporary addresses. So a device receives a prefix from the network and then fills in the remaining bits with temporary addresses with a limited lifetime. Here in an example, we have an IPv6 client that uses temporary IP-A and establish several flows towards the internet with that. What the RFC or the implementation do is that as long as the flows remain, as long as those red flows remain, IP-A is still used, and then at some point the IP expires and the new IP comes up. This is IP-B, the blue one. But IP-A will remain as long as there are flows that use it. And non-multipath transport protocols cannot migrate. This is kind of obvious. So the opposite of that would be to say that multipath transport protocol would help in this case to move the flows to the new temporary address more quickly. Next slide, please. Then on the server, there has been recently a proposal for adopting kind of a moving target defense with IPv6. This is kind of fun. It's called Choi Hopper. This is not work from the lab, but I took the idea just to explain it simply. So what it proposes is use a temporary IP for the server that is within a prefix, and this temporary IP is determined cryptographically. So given a shared key, a timestamp, and a salt that you choose, you get a random IP value. Random, I mean cryptographically random. And so if you share this shared key with the client by some ways, could be DNS for instance, then you're able to hop from one IP to another and kind of hide your server from scanners, from all those annoying researchers that try to understand what your service is doing and all of that kind of stuff. So here in the same way as on the client, the multipath transport protocols could help migrate your client flows towards the new addresses and keep your servers hidden in a sense. Next slide, please. So we've been also looking at load balancing, and we've been doing a simple prototype and try to see. So today's servers are very, very likely multi-core. And we started thinking, okay, does it help to put one IP per CPU core? And so instead of having one IP on the network interface, you would have several IPs, and each of the IPs correspond to a CPU core. And so we've been doing an experiment with Quick. So we had a setup in the lab with Quick and 128 clients that make repeated requests. So a lot of requests comes in every time for a certain amount of time. And we've been looking at how assigning one IP per core helps the load balancing. And in the graph, there is to box plot, there is one for one IP per core, and then one for single IP, which is a single IP on the network interface. And we've been observing that one IP per core could be a nice way to load balance the load of incoming clients. So the reason for that is that in the single IP case, when the NIX receives a packet, it will spread the packets it will spread the flows based on a hash. So it takes the packet header, does the hash, and then decides, okay, I'm going to assign this flow, this new incoming flow, to this core. And this is a time costly mechanism. In the one IP per core case, the clients use the DNS to select one of the server IP. And so this one stage of load balancing is kind of offloaded to the clients. And then on the NIC, it becomes much simpler because it's simply about looking at the IP and based on the IP, choose the core. So this is one step, but we could go further. Like many of the load balancing works from the academics that you probably know of have some sort of mechanism to spread the load further. So all the workloads are not the same. In our experiment here, the workloads were the same. So it's kind of a toy example. But if you want to spread further the load, you could use multipath transport protocols to transfer the flows to a different IP, meaning transferring the flows to a different core and help spread the load. Next slide, please. Lastly, one ID that is rather in the network rather than on the host. We've been looking at IDs on the host in this presentation, but there are more IDs in the network in the paper. So one of the IDs is combining IPv6 prefix and segment routing domains, and basically put all the related services inside an IPv6 prefix. This is kind of a simple ID, but it has the nice effect of for incoming traffic to be able to route the traffic through service chains just based on the destination IP. Next slide, please. And so that's some of the ID we've been exploring in the paper. But really, the key message of our position paper and this presentation is that with IPv6, we have a lot more addresses to play with, which doesn't necessarily mean we have the only way to use them is use more device. We could just simply reconsider how they're used on the device. And there is much more to do than just assigning one IP to each interface. And there could be a lot more thoughts in this direction to try to explore what all this means. And obviously, multipath transport protocol are quite useful on the end host to be able to leverage all those possibilities. So if you're interested in developing those use cases with multipath transport protocols and several IP addresses, just reach to us, myself, Olivier, or share any thoughts you have now. I think that's the end of my presentation. I'm ready to take questions. So.
I was first, abusing my chair power, putting myself in the queue. Thank you very much. Very interesting. Glad to see that someone else is trying to solve this multi-homing without a BGP on IPv6 stuff. One comment and one question. Actually, two comments and one question. First of all, yes, IPv6 basically already, right, by definition, any IP, almost any IPv6 enabled host will already have multiple addresses, right? Linked local, stable, privacy, multiple privacy, actually, right, and so on. You might be interested to go and to look into v6 ops thread going on, because I started some fire there by noticing that while it's all great, operationally, if you start using multiple addresses, now you're hitting some hidden limitations on which vendors tend to put on us. And some people actually in v6 ops might find your presentation quite scary, because as it's been correctly mentioned there, multiple addresses come in with a cost to the network. Because you need to have various types of caches on your network devices for every address. And if you talk about some VXLAN deployments, it's going to be actually a route per address. And when you move from one route per client to like 20 routes per client, you might actually go to a significant upgrade of your hardware. Question, so have you done any like practical testing on fallback speed, on switchover speed, if you have multiple addresses and like some of them do not work or stopped working in the middle of the session, which actually much worse?
So we're pretty early on the process of experimenting. So the quick answer is no, but we're looking to continue that work, and this is definitely the kind of question we would like to answer. We thought about how we could propose to the students on our campus to do experiment at their home and really have a lot of people toying with this on a practical level and see what are the drawbacks of having multiple addresses, how is the OS handling that, and that kind of stuff. So definitely, you talked about v6 ops. We are also interested not just on an academical level, but today what are the drawbacks, or what are the obstacles in the way to be able to use multiple addresses? Because I don't think many people have experience on that, practical deployments and stuff like that.
Thank you. So next in the queue, Luigi.
Yes, that's me. Hi. Thank you very much for the presentation. It was very interesting. My question is more about, are you just interested in developing use cases and in a certain way how you deploy and use IPv6 addresses? Or do you think we can go further and revise actually the IPv6 addressing model?
Apply that to the IPv6 address model, is that what you said?
Yeah,
Um,
to revise, I mean, the IPv6 addressing model, maybe making it evolve somehow.
So giving such advice is not an easy position. um, so my personal interest is rather in transport protocols. That's also
We can see that on the multipass side of the presentation.
But really, like in the paper, the discussion goes as further as do we need ports, or is IP address all enough? Can we address one IP address per process, and does that works? Obviously, from an operational point of view, it might seem complicated, but the concrete step for us is experimenting with all that rather than like proposing a new IPv6 addressing model. And I know there's been an addressing discussion in the IETF going on, but I've not looked at it, sadly.
If you want to look at
think
it,
you're
you
part
talk
of
to
it,
me,
right?
and I can send you a couple of pointers.
We might talk
and
more.
We will welcome any new idea there. Okay.
We might talk more offline of that then. Sure. Thank you.
Cool. Rio?
Hi. From the prior question, I figured that you are more interested in transport, and that's the sort of focus. So you haven't looked. Have you looked at anything sort of underneath the transport layer at the network layer, for example? Because at the end of the day, so it comes down to architectural naming issue where this is clear sort of semantic overloading of IP addresses, right? And IP addresses considered harmful, and then like this kind of paper have shown that. So my point is, it might be interesting for you to sort of look at the sort of cohesion of sort of say network layer sort of tidying up naming architecture approach at the same time as you look at the transport protocol, what the how like this identifier locator split network protocol, aware transport protocol might be something that might be fun to sort of explore. I've during my PhD I worked on sort of that sort of area, so might be good if we take this offline and chat more later, if that's
definitely. I talked about transport, but like we like root cause analysis in our lab, so definitely the network, if the network layer is involved and there are some impediments in the network layer, we're interested to know them. We're not just sitting on the transport layer.
Great.
But yeah, definitely.
Let's chat about this.
Okay, cool.
Me again. So idea of like address per application and using v6 addresses instead of ports, it's actually quite interesting one. I think if we want to go to that direction, we would need to change deployment model, specifically go to something like /64 per host, because otherwise, like, it does not scale. Because all these like addresses come in, as I said, with a price, and network probably, like current networks would not survive until you go to something what like 3GPP is doing, when from network perspective, it's still just a route. The networks are designed to deal with routes. And if you go in /64 per host and you give an host, the whole /64, do whatever you want with this, it will be host limitations, not like network limitations. So again, I guess transport people do not come to groups like v6 ops too often, but I suggest you might pay some attention to this. Thank you.
Very interesting comment. So yes, the intent was to give a /64 to the host. And I also just wanted to say that our knowledge is kind of textbook IPv6. So the network course is all IPv6, so that's the only thing we know. But from our university at least. But then so our understanding is kind of is that so IPv6 define prefixes. Prefixes are routed. Only routes to prefixes exist, but then in the reality there might be subtle things that we don't know of, and I'm pretty sure Olivier had some insight about that. But like the exploration of thoughts started from there, from this context.
So like there are some there is a devil in the details here. Yeah, but yeah, I guess we can talk more. Thank you.
Thank you.
Okay. Thank you. Jordi. Supporting. Wait. Do we have the right slide? So. Yeah.
It's the first one.
Is it the? It's the right one, right? Yeah. Okay.
Right, so thank you very much. I'm Jordi Ross from Qualcomm, and I'm going to be talking about bottleneck structures. I have a couple of presentations. The first one is provides the basics of bottleneck structures, interaction, and some of the use cases. And I'm going to talk a little bit about also production deployments. And then the second presentation after is going to be about how to compute bottleneck structures under partial information in the context of multi-domain or multi-autonomous systems. Next slide. Yeah, thanks. Next one. So I'm not going to go into the math, but basically you have papers. There's a SIGCOMM paper, SIGMatrix paper, an extended technical report also, and then a couple of drafts that you can read. The drafts, currently the discussion has been halved in the Alto working group, but I'm here more in the research group to also discuss, because applications of bottleneck structures could be within other working groups and research groups as well. So next up, yeah. Thanks. So I'm going to pick on, to start the introduction, I'm going to pick on one specific communication network problem, which is the problem of congestion control. So the prevailing view in the problem of congestion control has been based on this notion that the performance of a flow is uniquely determined by its bottleneck link. This sort of view goes all the way back to the famous Jacobson's SIGCOMM paper in 1988, which proposed the first congestion control algorithm with this diagram showing the notion of bottleneck link, which literally saved the internet from congestion collapse by proposing the first congestion control algorithm. Now, next slide. While this is a true statement that the performance of a flow is uniquely determined by its bottleneck link, what we find is that there is a more sort of fundamental or hidden story behind it. And the analogy that we'd like to build to understand what a bottleneck structure is that if the problem of congestion control were an iceberg, the notion that the performance of a flow is uniquely determined by its bottleneck link would be the symptom, the tip of the iceberg. What's underneath, what the submerged part, is what we will call the bottleneck structure, which is hidden, sort of latent, but reveals the sort of system-wide performance of the communication network system, right? So we'll see what that means in the next slides. Next. Now I'm going to sort of put an example to illustrate what a bottleneck structure is. So I'm going to start with the communication network, and this example circles are links. So we have 4 links. Link 1 through link 4, each one with a capacity, C1 through C4, and then lines are flows traversing the links. So we have 6 flows, each one with a color, so flow 1 through flow 6. So for instance, flow 1 traverses link 1 only, flow 6 traverses link 1, link 2, and link 3, and so on. Okay. Now, next slide. I'm going to fast forward and forget about the math, and I'm going to show you what the bottleneck structure is and how to interpret it. This is the bottleneck structure of this communication network configuration. And the way to read the bottleneck structure is as follows. So vertices, white vertices correspond to links. So we have link 1, link 2, link 3, and link 4 are 4 white vertices. Color vertices are flows. If there is a directed edge from a vertex, from a link vertex to a flow, it means that that flow is bottleneck at that link. So in this case, we have that flow 3 is bottleneck at link 1 because there is a directed edge from link 1 to flow 3. And the other relationship is as follows. If there is a directed edge from a flow to a link, then it simply means that that flow traverses that link. Right? So in this case, we have the flow 3 traverses link 2 because there is this relationship, and that's actually true. So flow 3 traverses link 2. and flow 3 also traverses link 1, so this is a bidirectional, but flow 3 is bottleneck at link 1, so there is also the direct attach from link 1 to flow 3, and so on. Okay, so that's the sort of the core relationships described by the bottleneck abstraction. And so you're going to start sort of thinking about what this is revealing us. So it's telling us where a flow is bottleneck, but also it's telling us more information. So if you want to click next, thanks. Now let's see how we sort of can start interpreting these. And one of the things that bottleneck structure reveals is how perturbations propagate. If there's a perturbation on this link, on link 2, say, maybe this is a wireless link, and so the signal to noise ratio is changing or something. The bottleneck structure tells us how it perturbates. So if you want to click on next, thanks. And it tells us that the propagation of this perturbation will propagate according to this D graph. And what that means is that it's going to have an effect on flow 4, flow 2, and flow 5, and link 3, but it's not going to have an effect on flow 1, flow 3, and flow 6 because there is no directed path from link 2 to any of these other regions of the network. So let's see how that works. So we say there's a perturbation on link 2, maybe a change of capacitor, then that's actually going to have effect of flow 5. Notice that flow 5 does not traverse link 2, but it's sort of interconnected, and that's going to propagate, right? We can also see other kind of relationships, and that's the reverse work. So for instance, this tells us that actually, if I perturbate flow 1 somehow, maybe let's say I traffic shade flow 1, or maybe flow 1 disappears. That's going to create a perturbation on the network. How will that propagate? Well, there's a path from flow 1 to flow 5, actually 2 paths. So that tells us that it's going to have an impact on flow 5. That's actually not trivial to the human eye, if you will, because flow 1 is actually on this region of the network. It's telling us that a perturbation on flow 1, say flow 1 disappears, that's actually going to have an effect on flow 5, which is not apparently related. But the reverse is not true. So if I actually change flow 5, maybe if flow 5 disappears, that's actually not going to have an effect on flow 1 because there is no path from flow 5 to flow 1, right? So you can start seeing that the graph is revealing some sort of hidden stories about how perturbations propagate through a network. Okay. I haven't told you how to complete the bottleneck structure, but that's in the paper. Maybe I'll omit that for this occasion. But if you want to click on the next one, now what I've been mentioning so far is sort of like qualitative analysis of the network. I've been telling you about relationships, how perturbations propagate, right? But one thing about bottleneck structures, actually, they allow us to compute things. And that's what we call the quantitative theory of bottleneck structures. We can actually quantify these. So if there's a change on the capacity of link 2 by certain magnitude, how is that change going to propagate, and what's the throughput that's going to be, what's the effect on flow 5 in terms of throughput and so on, right? So we can actually quantify these. I'm not going to go into what these numbers are, but we can actually quantify. And this there's a conversation about, can we sort of use this to compute a path metric? That's sort of the connections with PANRG we're going to try to build, that we could actually use some of these numbers to put them as path metrics, and we'll sort of also build that story in the next presentation. But the point about this is that you can actually qualify, but also quantify these relationships using the bottleneck structure. So if you want to click on next, thanks. Okay, so now, can the flap of a butterfly's wings in America set off a tornado in Asia? Of course, the answer is no, but everything is interrelated, and even the flapping of the wings should have an effect in somewhere in China, right? And that's the point. And that's sort of what bottleneck structures sort of capture, this idea that everything is integrated, and how this, how things correlate in the structure of bottlenecks that is latent in a communication system. So next one. Okay, and then I'll just summarize sort of what I say informally, a little bit more formally, not too much, but this is what we call the propagation lemmas. And when it goes as follows: if a flow F can influence, we say that a flow F can influence the performance of another flow F prime, even only if the bottleneck structure has a directed path from F to F prime. And this works for flows, links, and interleaved as well. So in this case, let's say there's a perturbation in this flow. Let's say we traffic shade the flow, or the flow disappears from the network. You're going to click on next. Thanks. Then this portion of the network will be affected, but these other flows will not be affected. Same thing if you, next one. If there's a perturbation in the capacity of this link, then next. This portion of the network will be affected again, but not this portion of the network, right? So this is how it sort of works. And then next one. Okay, and so you can actually, I mentioned you can quantify these things. So this is what we call the link and flow equations, and this tells us how these perturbations propagate and in which quantity they propagate. These are the equations. I will not go into it, but one of the points I will make about this, if you want to click on next, yeah, is that the bottleneck structures actually effectively are computational graphs. And so that's one of the advantages, not sort of the framework that provides us, but actually they allow us to make these calculations very fast, actually, because a perturbation is really a derivative. When you perturbate the flow, you're really, and measure the effect of that, you're really computing the derivatives with respect to that small change on that flow, right? So it's a tool to actually compute derivatives. And so once we have a tool to compute derivatives, we have a tool to optimize communication systems. And that's sort of the whole point, that we can use bottleneck structures as a framework to optimize communication networks. And we'll see the applications that have in a couple of slides, I guess. But the bottom line is that we can use this computational graph, bottleneck structure, to compute gradients. And this is an example. And an analogy for those maybe who are more versed on the AI field is that really a computational network is like a neural network. There's a computational graph. And so you can sort of can actually do backward and forward prop computations on it to compute in one scan of the graphs all the derivatives, and sort of you can start thinking about how we can use this, the graph to actually do very scalable calculations. If you're trying to find ways to optimize your network, in one scan of the graph, you can actually compute all the derivatives and then sort of get that result. Otherwise, that might be sort of unscalable using other tools. This also connects to the field of automatic differentiation, where you can actually compute these derivatives fast, but also accurate, as opposed to using limits, which is numerically unstable. But with the computational graph, you can actually use AV to make these calculations without error, actually, with 100% precision. So if you want to click on next. Thank you. Yeah, so let's put an example. And I'm going to use the same example. And I'm going to query the framework, the theory, and ask the following question. I have this network, and I want to choose a flow that when I remove it from the network, total throughput increases maximally. And I'm going to assume that the flows are regulated by congestion control. I'm going to do the simulation using BBR later, but I'm going to sort of query the system, say which of the flows is such that when I remove the flow, I get maximal in total throughput improvement on the network. It's sort of like finding the elephant flow, if you will, which is the flow that has the highest impact on the network. So if we actually, and then we can use bottleneck structures to actually do this. And if you click on next, then you can, we can scan the graph, compute the derivatives, and we obtain these derivatives. Capital F is total throughput. So what I'm doing here is, or what we're doing here is computing the derivatives of total throughput with respect to changing the rate of a flow, which could be flow 1, 2, 3, 4, 5, and 6. And then I'll pick the one that has the smallest value, actually, in this case, the smallest negative value. Because what I want is when I reduce the rate of a flow, I want to increase maximally the throughput, right? So it has to be a negative derivative. And so if you look at the smallest value possible, is this one. So it's revealing us that the sort of elephant flow, the flow that has the highest impact on total throughput of the system, would be actually flow 6. This may not be necessarily trivial. If you look at what elephant flow detection algorithms do, they typically focus on the heavy hitter flow. The heavy hitter flow here, this is the throughput of each flow, actually. The heavy hitter would be flow 5, which is getting 75 megabits per second. And it's telling us that actually flow 6, which is only getting 8.3 megabits per second, is actually the elephant flow here. And it may not be trivial to know, human eye, but it's sort of, you look at the graph, then it starts making sense, because flow 6 is here, and it's highly strategic flow that's sort of traversing the core of the network. And so that starts to make sense of why flow 6 has such an impact. So if you want to click on next, and indeed, flow 6 sort of here is very strategic on the graph. This is the computation. This is the bottleneck structure. You can see that indeed this is the reason why this is a high impact flow, even though it's getting low bandwidth. This is the actual simulation showing that this indeed happens. This is running the network that I just showed with all the 6 flows. You get this performance. So that the purple flow is the heavy hitter flow, the big flow. When I remove the heavy hitter flow, which is flow 5, is sitting here in the bottleneck structure, we know from the theory that this has no effect on everyone else, because there is no path from flow 5 to anywhere else. And indeed, that's what we see. We remove the purple flow, and the rest of the flows actually experience no change. They all have the same completion time. But if instead I remove flow 6, which is this flow here, this flow here, one of these flows here, actually then we see that completion time, everyone is getting more throughput, and the completion time of the whole execution here is reduced from 679 to 457, right? So by removing the mouse flow, actually in this case, we get maximum increase in total throughput, if that's what we care about, say, right? So you can start seeing some of the insights that the bottleneck structure provides in this, for example, if you will. Okay, then, all right. So, types of perturbation supported by bottleneck structure. Remember, a perturbation is a derivative, right? Is a types of derivatives that you can compute. Flow routing, traffic shaping, link capacity upgrades, link capacity fluctuations, path shortcuts, flow scheduling, flow completion, job mapping. Say you want to map a neural network on a data center, say. Multi-job scheduling. These are some examples of how you could actually use bottleneck structures to sort of optimize these kind of problems by computing these kind of perturbations. These are all perturbations on a system. When you place a job, that's a perturbation. How does that affect the system? And next one. Okay, then I'll talk a little bit about use cases again. And so, yeah, thanks. And so there's this sort of tree here that, bottleneck structure at the root, and then what are the applications? We like to think about three main branches: network design, traffic engineering, AI. Even you can see some of the applications: 5G resource allocation, flow performance prediction, network modeling, slicing, routing, congestion control, network resilience, capacity planning, robustness analysis, data center design, on-chip networks, even modeling simulation. These are some of the applications that we're actually working on, and some of them are being sort of researched. And I put a list of potential research groups maybe that could right now, like I said, we're in the Alto working group, but by coming here more in the research side, I hope to get feedback on where some of these things could potentially have a contribution in some of the research groups or working groups that you guys are working on. So then next one, thanks. And then in the draft that we have in the Alto working group, there are two drafts right now. The first draft, we mentioned a few use cases. So application rate limiting for CDN in edge cloud applications, time-bound constraint flow acceleration for large data sets, performance optimization through AI modeling, joint routing congestion control, service placement in edge computing, training neural networks, mapping a neural network on a GPU cluster or data center, and network slicing. These are use cases that we elaborate a little bit more. So if you're interested, you can go to the draft and see how we think that bottleneck structures could help there. And then I'm going to pick on one example, which is optimizing routing and congestion control. That's also from the draft. So let's see one specific example. Yeah. Thanks. So this example focuses on Google's B4 network from the SIGCOMM paper. So this is each of these nodes is a data center, and that's the interconnect. This is the adjacency matrix. You want to click on next. That's the same thing, a little bit more human-friendly, which is Google's B4 network from the SIGCOMM paper, and how it's interconnected. Okay, so we're going to apply a bottleneck structure here to reason about some of the insights from this network. You want to click on next. Yeah, and so assume a simple configuration with a pair of flows between every data center in the US and Europe. We're going to keep this really simple. All links are assumed to have a capacity of 10 gigs, except for the transatlantic links that are at 25 gig. If with these two assumptions, then we complete the bottleneck structure and we obtain this bottleneck structure. Okay. If we click on next, that's a little bit more graphical. Then that's what we obtain. This is the bottleneck structure. Here we have white vertices are links. So if you want to click on next to, and then gray vertices are flows or paths. And here, so there's some mapping. So these two transatlantic links, link 8 and link 10, would be sitting at this location, the bottleneck structure, link 8 and link 10. And these two other links here will be sitting at this location in the bottleneck structure. We are representing here the bottleneck structure in what we call a canonical form, where it's sort of like the direction of the edges always go down, not up, unless they are bidirectional. And so there's this property, this lemma that we show also in the paper, that the available bandwidth is monotonically increasing as you go down the graph. So the flows at the bottom of the graph will tend to have more bandwidth, or the paths at the bottom of the graph will have more bandwidth. You can see that I'm changing flows and path interchangeably. I haven't mentioned this, but there's a version of the bottleneck structure which we call path grading graph, which is folding all the flows that follow the same path into a path. And you can do the same reasoning changing flows or paths. And I think that's for PANRG, that could be more interesting because we really want to talk about paths, I think. But sorry, I think I think that's right. So, but what I wanted to say about this is that you can see that these two links actually somehow in the US are highly strategic because they are at the top, at the root of the graph. This means that any perturbations on the capacity of these links will actually have an effect on the rest of the network actually. And this is not true for these other links that are at the bottom, that really they are not so strategic because perturbations of these links will not have the same effect. So that's kind of like the qualitative reasoning about this setting, okay? Now the question is, okay, I want to transfer, suppose that an application needs, or a data center needs to transfer, you know, a data set, sort of a large data set from data center 11 to data center 4, right? And we need to decide which path to choose. And we have multiple path options. And so then what we can do here is around bottleneck structures and figure out what bandwidth we'll get on each of these paths. And the idea here is what we're doing here is it's sort of solving the joint congestion control and routing at the same time. It's asking the question, if I place a flow on this path, what's the bandwidth that this path will get? And what is the path that all the other paths will get? So the ripple effect, the exposed result. I don't want, after I place it, what is the actual performance I'm going to get? Because placing that flow itself is going to have an effect on the network. So how is that ripple effect computed? So that's what we can do using bottleneck structures. There's an algorithm to actually solve this problem, which actually combines Dijkstra with bottleneck structures. So Dijkstra is a greedy algorithm. So every step is actually querying the bottleneck structure and building the bottleneck structure in parallel to discard paths that would never be optimal using the greedy Dijkstra approach. And so that's why the complexity of this algorithm is V plus E log V, traditional Dijkstra bound. And then we get this result. In this case, we get that this is the optimal path, and we'll give you 2.5 gigabits per second as predicted by the bottleneck structure. And this is a non-shortest path, actually, that gives you higher throughput. If you actually use the shortest path, you will get 1.4 gigabits per second of throughput. So then you can decide whether you want the high throughput path or the low latency path, but you can make that based on an informed decision. You can also use this for SLA management. So because what we can do, like I mentioned, once you place that flow, you can see how the rest of the flows will be affected. Will they have a violation in the SLA? So before I place that flow, I want to make sure that that will not violate SLA agreements on other paths, say, right? So that's the kind of idea. Yeah, next, thanks. And this is sort of the result here. So we're using bottleneck structures to project what will happen if you place the flow on the shortest path or not the shortest path, or the non-shortest path. On the shortest path, which is lower throughput 1.4, you would place it here at the top. Actually, when you do that, the flow would go right here at the first level. If you place it on the non-shortest path, the flow would be placed here. And that's, remember, the monotonic property. If you place something at the bottom, you get more throughput. That's what's happening here. So the recommendation, if you care about throughput here, is to place it on the non-shortest path, which will give you 2.5 of throughput as opposed to 1.4. Then you can do the SLA management sort of thing, and then say if you want to go next. And then this is the ripple effect. If I place the flow here using the shortest path, the red circles are the portions of the network that will see an impact. If I place it on the non-shortest path, the green circles are the ones that will have an impact. So you can see that actually the impact is smaller because we're placing the flow at the bottom of the graph, so they were influencing less others. So it's kind of also more stable maybe, as opposed to here that's creating a ripple effect much bigger in the whole network. And then next one is this idea that I mentioned that, as I mentioned, that this monotonic property, that the flows at the top are getting less bandwidth, or the paths at the top are getting less bandwidth than the ones at the bottom. If I place the flow on the top, I'm still in bandwidth from the ones that are getting less bandwidth. So you could reason that maybe that's not a fair thing to do, because all these flows at the top who were already getting low bandwidth are going to get even less bandwidth. But if I place the flow at the second level, these flows have see no impact. Right, so their low rate does not get deteriorated any farther, and so maybe that's from a fairness standpoint. You can also reason that it's also good to actually push the flow to the lower level because you get more throughput, and you're not going to have the flows that actually have less throughput. And yeah, I think that pretty much covers it. I want to put a note on. We have two production deployments, and on this one is at the National Research Platform, which is a US-wide network. Used to be called the Pacific Research Platform at UCSD. A network connecting the Pacific and the west side in the US, connecting the universities and research labs. Now it's called NRP. It's a US-wide network, like I mentioned. And then the other one is the DOE ESNet, which I'm sure many of you know also. which is a US-wide network connecting also national labs, etc. So one application we're using for the ESNet is capacity planning. The other, but we're also looking at traffic engineering. And so, for lack of time, we will not go into deployments today, but maybe some other time we can discuss deployments. And I'm happy to take questions.
Sorry, Jerry, we actually have time. So if you want to talk about something.
Yeah. We can leave it for the Q&A if people have questions.
I was going to ask that question, so we'll leave it for the Q&A.
Cool. Yeah. So
wait, we already have Antoine?
Yes, I think that's the last one.
Okay.
Yeah, discussion. And one note on discussion, I'd love to get, or would love to get feedback in terms of where we think this could connect with other working groups or research groups. So that's one topic of discussion, but it's open for any other questions as well, of course. Mm-hmm.
Hello, Antoine Sanko. So I have a question, but more on the graphs you are using rather than on the working groups. I won't help you on that. In fact, when I looked at your graph for bottlenecks and how you...
Sorry,
So when I look at your graph with flows that are nodes, but you also have nodes that the flows go across that are represented as nodes, it reminded me of the work of Mathieu Latapi, a researcher in France working on some tool called stream graphs. It's a sort of mix between time series and graph, and you have mathematical tools that help you associate properties to the temporality of where flows cross some nodes in the network. So I think it would be beneficial to your work to look at this abstraction, because I think this typically applies to what you are doing.
Okay. Okay, good. I'll look forward to talking about that. Yeah, very nice. Thanks.
Roland Blesk, TE. Thanks, great work. Sounds very interesting to me. Maybe ICCRG is a good place also to come to. So because probably we have to think about different ways of doing congestion control, in the sense that maybe the current closed loop congestion controls are some kind of last resort, but we come more into a direction of having better planning so that you can ramp up flows very early, for example. And with your framework, one could actually see the effect. If I admit a certain flow, what happens? And is it better maybe to rate limit that flow, or just don't have it at all? And so on. So I think this is quite useful.
Got it. Thank you. Yeah, the next presentation is I'm going to talk about how to do this under partial information. And the case of ICCRG, I think, or congestion control in general, can be seen as a specific case of partial information, because in the distributed congestion control algorithm, every node has partial information. They're all trying to converge to optimality, basically. So that probably can enable another conversation. But yeah, thanks.
So yeah, Brian Trammell as an individual, not as PANRG chair. So I had one question that I missed at the beginning of the presentation and I should have stopped you, but now I'm going to have to go back and rewatch on 0.75 speed. But so the difference between an edge that is unidirectional and bidirectional, right? How do we, when we're going through and actually constructing this graph, how do I know I'm putting two arrows on it?
So you have two arrows when, actually, whenever you're bottleneck somewhere, you have two arrows. It's bidirectional. The reason is because if you're bottleneck there, you're crossing that link.
Got it. Okay. Good. Okay.
Yeah.
Wow. The rest of the talk makes a lot more sense now. Cool. Thank you very much.
Cool.
The second thing that, riffing off of Roland's point a little bit, I did very much have the feeling that I was watching an ICCRG talk here, which is great because I missed ICCRG this time. So thank you very much for bringing this PANRG. I think a lot of the questions about sort of computing the optimality, that's a good venue to get good feedback on that and sort of develop the idea there. The thing that I would be interested in seeing in PANRG is okay, so we have this mathematical tool. How can we, I'm going to go ahead and take the mask off so you can watch my mouth moving. How can we tie that to some of the signaling stuff that we're thinking about in PANRG, right? you brought up the B4 graph from the SIGCOMM paper, which is like, okay, well, you can very clearly see how this would be used in a centralized planning SDN, SD-WAN situation. I think you're probably going to answer some of my questions in the next talk. So I'll probably re-ask the question then. Is like, I'm really interested in then how to tie that partial knowledge situation into what signaling we would need in a path-aware internetwork. So
Yeah.
yes,
I think the next one we'll probably shed some light
Perfect.
on that and maybe more questions. Yeah.
Thank
cool.
you.
Mhm. Okay, so then the second part is about, okay, we know what the bottleneck structure is at some level, and we'd like to actually be a little bit more practical, and one way to make this practical is, okay, how do we implement this under partial information, which is typically the scenarios that we face in a communication system where you don't know everything, but you still have to make the best you can based on the information that you have. So let's talk about this a little bit. And I'll skip the first part. Actually, we've done that, so checkbox. But then we'll talk about computing bottleneck structures under partial information. I'll talk about the distributed border protocol that would allow us to do that, the signaling part, if you will. And I'll put that in. I'll illustrate how this protocol will work and achieve global conversions, and then discussion. Right. Next one. Yeah, same theme, papers and drafts. Next one. You can actually skip this. Yeah, sorry. Move on. More. Sorry. Thank you. Yeah. Okay. So now remember, I'm going to actually use the same example. So hopefully we're a little bit familiarized. The same network configuration, but so far we've assumed that we have full knowledge of the network, right? Now let's assume that that's not the case, and let's assume that we have two autonomous systems. So if you click on next. Okay, so we know that this is the bottleneck structure. We have full knowledge, but if we click on next, now we're going to assume that this network actually corresponds to two autonomous systems, and each AS knows only its own region. So AS1 doesn't have any information about AS2. AS2 doesn't have any information about AS1. Now we run the algorithm, so you can click on next. We run the bottleneck structure algorithm that's in the paper to compute the bottleneck structure. AS1 would converge to this, would think that this is the view of the world, this is the state of the world, this graph. But obviously, based on this, this is AS1. So no, this is actually AS2. Oh, this is the old presentation actually. Somehow.
Do we have to do a reload?
Yeah. So okay. So it is.
If not, that's fine. We can probably
No.
figure it out.
Quick reload up there.
I think you got it. You got it uploaded. Yeah.
Okay. Let's see if we can. Okay. Hold on.
That's all actually.
Hold on just a second. Let me see what we got.
I think it's fine.
Okay, well, I can try again. Just a second. Meeting materials.
Yeah, I don't have any pending unapproved
No, I was
slides.
uploading from email.
Okay. Yeah.
But I quite sure I. Okay. Let's see. Which slide is that? Is it still old one, right?
That looks like the last one.
Yeah, it should be instead of floors, but otherwise you have a P or F.
Those are Fs.
Fs, yeah. So.
Okay, let me.
Is it a serious content problem?
No.
Okay. Yeah. Let's.
Okay.
let's move on then, and then we'll
okay.
upload the correct one.
Whenever you see an F, should be a P, and the latest, and we'll get the latest updated on the because it works for paths basically. And so instead of flows, these are paths. So AS1 doesn't know anything about AS2, and vice versa. So if AS, and this is also swap. So if AS2 tries to figure out the bottleneck structure, it will compute this, which is incorrect, right? This is not the same as this. And if AS1 actually this swap computes the bottleneck structure, actually it will compute the right thing actually, but it's because it got lucky. Because there is this property that if a path is bottleneck, if all the paths are bottleneck in my autonomous system, then I'm able to compute the bottleneck structure with any information from anybody else. And that's what's happening here with AS1. Actually, this is AS1. That actually it happens that all the paths in AS1 are bottlenecked in AS1, so then it actually can converge. But it's because it got lucky. And AS2 actually the paths are not bottlenecked in AS2, so it's not gonna get it right. So obviously we need to share some information to make this work. So we can click on next, and the proposed protocol here has these three properties. Convergence, which is the key idea, but sharing one metric per path is enough to ensure convergence to the correct bottleneck substructures. Here I'm introducing some terminology. The global one, we call it bottleneck structure, and then each AS has a bottleneck substructure. And the idea is that we want each AS to compute the bottleneck substructure that's correct. What is the correct bottleneck substructure? Is the subset of the bottleneck structure that corresponds to that AS, basically, intuitively. So, and then this is saying that all we need to do is share a path metric, which I'll tell you in a minute what that is. Scalability, focus on building the path gradient graph. So here's another thing that we describe in the draft. Bottleneck structures, there are different kinds of bottleneck structures. One is what we call the flow gradient graph, which is per flow, but this one which is called path gradient graph, which is per path, and that's way more scalable because you may have hundreds of paths as opposed to millions of flows, and the transition from one to the other is straightforward actually. So for this we focus on path gradient graph, and so requires only per path state in this case, not per flow. And then privacy, this is subject to discussion I guess, but we think that this could be good in the sense that we only need to share one scalar, one metric per path. We don't need to reveal flow information. There's no need to reveal net flow data or topology data. All we need to share is a metric, a scalar per path. So hopefully this is good in terms of the privacy, depending on the use case. So next one, then this is the distributed protocol. It's in the second draft. And I'll go these at a high level. I don't expect maybe to understand all the details, but the intuition, and it's actually fairly straightforward. That's the good thing. So it has an event timer and a message event, a message exchange event. The timer is run periodically. That's run. These two events are run. Each AS runs their own instantiation. The first thing we do is some notation that's introduced in the draft. L is a set of links. AI is the autonomous system I. So this runs for each AI. PL is the path link dictionary, what we call the path link dictionary. For every path, the set of links that path traverses. C is a capacity dictionary, the capacity of each link. And PM is the path metric dictionary, which reveals the information we received from our neighbors. Okay, so this sort of includes the global information that we're collecting by talking with our neighbors, and this is sort of like the local information that we have. What this does is compute bottleneck substructure, which is a function that's in the next slide. The idea is that it tries to compute the bottleneck substructure as accurately as it can based on the local information that we have and this path metric that we're receiving from the neighbors. Once the output of this, then we consolidate it into the new path metric dictionary. This is what we're going to be sharing with our neighbors. And then here in the next step, we actually share it with our neighbors. We share the output of our computation into the path metric, and then we share it with the neighbors. For all AJ in N, these are the neighbors. We're sharing the path. We're sending a path metric announcement message to our neighbors, passing our path metric vector dictionary. And then this is the event upon receiving a path metric announcement from our neighbor. We simply take the minimum actually. This is the notion that the bottleneck is always the minimum. This goes back to Jacobson's paper that all we care is the single bottleneck, the most constrained link, right? So that's embedded in this notion, but this is taking into account the fuller structure. And then if we want to zoom into this function, complete bottleneck substructure, that's the next slide. And what it does is this complete bottleneck substructure, it runs this while loop, which invokes at every iteration the complete bottleneck as structure. Sort of that's again the one that's available in the paper, and it runs multiple times until it reaches agreement with the state that we are being shared from our neighbors. That's the intuition. So we computed complete bottleneck structure based on the link dictionary, the path link dictionary, and the capacity vector or dictionary. Here we check if the idea about this is the output of our computation, our log computation, is in agreement with what we're being told from our neighbors, then we're good. We break, we're out. If not, then we need to do something, which is we need to add a virtual link. We don't know our neighbor's network. We're going to model that by putting a virtual link and putting a constraint there. That's what it's doing, is adding a virtual link with a capacity equal to the path metric that's provided by the neighbor AS. And then we go back, and if it can be proven, that's sort of the math, that if you do this over and over, eventually everyone will converge to the right bottleneck substructure. When you aggregate them, you get the right global bottleneck structure. We can see with an example, maybe it's going to be easier to understand, but hopefully that's the intuition about the signaling. So and then before putting the example, what we call the termination condition and the convergence condition. In the previous function, you saw that there was termination, a break. It was a while true, but there was a break statement. The termination condition is when, intuitively, it says that when my local computation is in agreement with the path metric dictionary that's being shared with my neighbors, when we are all in agreement, and we can terminate. And then the convergence condition, what it says is that if you run this algorithm, we ensure that at the end, everyone is in agreement. All the path metrics from all the AA, from all the autonomous systems, AI, AJ, for all the paths, are in agreement. That's guaranteed by the algorithm. Okay, so we have these two conditions. Let's look at an example how this works. So back to our configuration. So two autonomous systems. We can click on next. This will be iteration 1. And again, this the latest version is going to have some corrections on this, but it's fine. At the first iteration, autonomous system 2 actually gets it wrong. This is the path metric dictionary that it believes is the sort of the state of the wall, but it's wrong. And then at iteration 1, autonomous system 1, actually this swap, actually gets it right. And the reason is that property that I mentioned, because all the paths are actually bottleneck in its own domain, so he actually gets it, or the AS actually gets it right. So this one has already converged. Now they exchange the path metric, so this path metric dictionary is going to be shared with this AS. Now, with that information, for AS2 is going to take another iteration. So if you click on next, and then in the next iteration, actually, the AS is going to get it right. Okay. So, and the trick here is, remember, we are adding this virtual. So we don't know that our neighbor, but we know that this path is bottleneck. This path 4 is bottleneck somewhere else. So we model that by using a virtual node here. And this path 6 is bottleneck somewhere else. We model that with another virtual node. And then this, if you look at this structure, you add this with this, you get the correct bottleneck structure. So if you click on next, then we can also see that we can now check the convergence condition and check that all the path metrics for all the path metric dictionaries from the two ASs are in agreement. So 16.16, 8.3, 8.3, and so on. Okay, so then next, and this is sort of the high level idea that you would have multiple ASs, each one doing its bottleneck substructure calculation, and then sharing these path metric announcement messages, path metric announcement packet, providing the AS ID and the path metric dictionary, and then ensuring that this, if the network stabilizes, then you eventually the bottleneck structure, everyone gets it right. And I think that's it. And then the same discussion can be open in terms of potential applications or questions.
Roland is making his way to the mic.
Roland Bliss, KIT. I think two comments here. One is maybe I'm not sure that actually the ASs or providers will be that candid in exposing that they have a bottleneck inside their AS. That is maybe one thing that could be a little pushback for that. And the other thing is, so let's assume that you know that paths are congested, then probably your whatever routing decision will then be based on that. And we all know that if you do, let's say, routing based on dynamic metrics like this one, where you have latency or congestion, that will lead typically to oscillations, at least in several cases. So have you thought about what, it is not totally clear to me what you want to do with that outcome, that you identify what are the bottleneck AS paths. So what's the reaction to that? Do you consider a system where end systems are able to choose a different path, or?
Okay, so on the first question, so actually this doesn't reveal that that this path is bottleneck at my AS. Actually, you could reveal it if you want to do that, but you can keep that privacy. What it reveals is that what the AS ends up knowing is whether I am the bottleneck for this path or not. That for sure. So we certainly, and then if I'm not the bottleneck, I know that's somewhere else, but I don't know where. Some other AS. Now, if you want to do the SLA management and you could envision an overlaying protocol that then sort of hot potato and say, I'm not the bottleneck, and eventually would find who is the bottleneck. But if you're not interested, you may not participate, and you would not be revealing that you are the bottleneck. If you're not interested, you could, but it's only an option to reveal whether you are the bottleneck. What you get is the information that this path is actually bottleneck on my domain, and if not, I don't know where it's bottleneck. And I think the second question is the one about not just qualifying these relationships, but also quantifying them. The idea about computing the bottleneck structure is not just to know whether I'm bottleneck or not, but to use it to do traffic engineering. Once you have the bottleneck structure, now you can start computing derivatives on that and figuring out if I place a flow on this network, what's the expected performance of that.
Yeah.
And so that's
okay. Yeah.
Okay. So that's the sort of the idea that we want to compute this bottleneck structure so that then we can do the sort of the derivative analysis on top based on that without knowing other people's other networks bottleneck structure, but still being practical.
Yeah. Okay. Thanks.
Okay.
So yes, Brian Trammell, as an individual again, thank you, Roland, for actually asking half the questions I was going to ask. I think there's another way that we can consider, like there's also a scalability problem here, right? Like, so you build the scaling of the convergence of the inter-AS path has to do with the number of ASs in the full network, right? Like, so this is a toy example that you worked us through, and the number of paths or the number of edges in the bottleneck graph inside each AS. And I haven't done the math because I'm sitting up here at the front, but it feels very much like this scales extremely superlinearly.
Let me try to see. Let's show the bottleneck structure. Let's talk about conversion. Let's talk about how it actually converges. So let's go back, more. Let's show the global bottleneck structure. More.
Until we get to the next
here.
Yeah.
The convergence time is revealed by the bottleneck structure itself. And it works as follows. So there are 6 paths here, right? The first to converge will be path 1, path 3, and path 6 will converge immediately because they have no dependency with anybody else. Once these 3 paths converge, then flow 2 and flow 4 can converge. Once flow 2 and flow 4 can converge, flow 5 can converge. So this is 3 iterations really. It's log. It's typically logarithmic because it's a graph.
Right. So the convergence complexity is basically solely dependent on the bottleneck structure, not on how you split it up into ASs.
Correct.
Okay. One of the tricks that we've seen in other path-aware networking approaches, I'm thinking about Scion here mainly, is when you end up with a substructure that is approaching too complex for the algorithm that you're using in order to figure out the route or whatever, you can abstract it away, right? Like, so the way that Scion does this is you can essentially take an AS and you collapse it down so it looks like a switch, right? And I'm actually wondering if there are ways that you could iteratively do that within an AS so that you get a very simplified substructure so that the overall structure gets you nearly an optimal result with way fewer nodes.
Yeah. So then we go forward. I wonder whether that captures it. So you can tell me, Brian. More forward here. So this is exactly, I think, what we're doing. What this is doing here, in that here you can see V2 and V1. What they're doing, they are collapsing into a single virtual node.
Yep.
We don't know what that is.
Yes.
It turns out that V2 and V1 are an AS. But we don't know. For us, these are two different black boxes. Right. But we know the path metrics that we know their path metrics, but we don't know anything else.
Right. Okay. Cool. Thank you for walking me through that.
Okay. Mm-hmm.
Any other questions? Good. Okay. Thank you very much, Jordi. So, Fenlin, I guess you are remote. I'm getting the slides. Hopefully.
Okay, can you hear me?
Yes, we can hear you.
Okay, thank you. So I will start. So good morning, respectful colleagues and experts, and with great honor and sincerity, and on behalf of my group and DT Corporation, I'd like to share our related work and perceptions on service provisioning of the network. And the topic I'd like to introduce is database-based open resource service, which is known as DBONS, the framework, use cases, and requirements. And next slide, please. So far, we proposed drafts and requirements in framework of DBONS as listed here, which illustrates the background information and the pivots perceptions. And our considerations begin with the challenges of the current network and the gap analysis of existing issues. And next slide, please. With the rapid development in the comprehensive utilization of cloud computing and mobile internet, cloud becomes a popular and major platform for various enterprises and government departments to host data and applications. So data explosion and massive access to the cloud have been proved to be an inevitable inclination, resulting in accelerating growth of traffic traversing through the network domain. So as depicted here in this figure, the network domain from Ningxia to Guizhou is divided into several sections and multiple routing paths. The network infrastructure in different sections may vary from one to another, which results in distinctions of network capabilities. Applications may require diversified requirements of latency bandwidth or flexible and comprehensive demands, like here, application A, B, C here. Here, A requires high bandwidth, B demands low latency, while application C requires both requirements. And ideally, traffic of distinctive applications from PE near Ningxia to another PE near Guizhou should be steered respectively into paths shown here in different colors. However, in conventional networks, visit details including path distances and section bandwidth in the network domain concealed, capabilities of the network remain invisible, and those differentiated services are not provided. Applications with various requirements cannot be distinguished and served customarily. Latency-sensitive applications could misunderstand that the bottleneck of the traffic is a restricted bandwidth from Ningxia to Gansu, which is 20G. However, in fact, the difference in different paths through Sichuan and Ningxia is over 200 kilometers, which is here 869 and 626. which results in apparent delay, and so fine granularity services can hardly be provided for applications. Next slide, please. And what's more, another occasion of the traffic from Gansu to Liaoning, due to the bandwidth restrictions in the Shanxi, Hebei, and Hebei-Liaoning sections, the bandwidth of the overall path along Shanxi and Hebei is confined, despite the sectional bandwidth from Gansu to Shanxi reaches 100 G. And the sectional resources are kindly wasted, and the overall utilization is relatively low. With ideal conditions supposed, other sections could be utilized and the traffic could be steered intellectually. And next slide, please. To sum up, conventional networks only provide clients with coarse-grained connection services, and differentiated service treatment is desired under current circumstances. The network resources are not orchestrated properly, and for example, in China, the resource utilization proved to be relatively low, about 30% to 50%. Existing issues like SD1 handles the problem by monitoring the latency of multiple bucket paths and applying a dynamic multipath optimization algorithm. And however, it requires traffic detection techniques and accuracy, and immediacy can also be guaranteed simply by collected statistics. Thus, when instantaneous jitter occurs on a monitored link, the current traffic is usually switched over to a standby path, which results in a waste. Furthermore, the introduction of network probing schemes also exerts extra burden on the network. S1 is capable of configuring different priorities in accordance with requirements from the client and further generates and publishes the corresponding QoS policies to ensure service delivery. Latency-sensitive traffic such as voice over Internet Protocol and web conferencing meeting are configured with higher priority and is further steered into specific path with better performance, while services like file backups are assigned lower priority since they are less time sensitive and may even result in blocks on network links. For dedicated lines usually configured between data centers to ensure network quality, in another scenario, it is relatively costly, and the period of service deployment and provisioning is comparatively long. Delays, packet losses, and interruptions also occur. So, with a conclusive view, fine granularity services and network resources utilization enhancements are urgently required. And next slide, please. Besides bandwidth, for instance, present network has also been endowed with various other capabilities, including deterministic quality, network slicing, endogenous security, etc., which can be delivered as services. Referring to software as a service, SaaS, a database-based open resource service framework, is proposed, aiming to practice the concept of NaaS, namely Network as a Service. With services reserved applications, cloud terminal, and CPE to subscribe corresponding customized network services. Next slide, please. In the framework of DBONAS, the network controller collects the running status of the network and abstracts network functions by extracting key attributes, including VD-link, VT-link nodes, and EP links. In particular, information includes descriptors of head node and head tail node in a real layer 3 link, IDP routes, identifier, a terminal system index, etc. A distributed database is also introduced here, which sustains strong consistency, and a typical subscribe-publish mechanism is applied. Capabilities can be abstracted in a key value scheme, and a standard schema template file is utilized for descriptions. The cloud controller or super orchestrator further subscribes the updated information of services published with a watch mechanism is performed, which enhances the efficiency of information advertisement. With the knowledge of network capabilities, path calculation can be performed and services can be re-orchestrated and bound with specific policies. Also, with database clients writing updated information, path degradation can be reflected and learned. Next slide, please. To illustrate this explicit process, we here present a detailed instance. The network communicates various clouds and multiple applications. Data center interconnection and cloud access from various applications are assumed to be typical scenarios. And in the overall network domain, here A, B, C, and D construct part of the physical topology. Policies identified by binding seeds are also assigned here. Path, network resources, and capabilities are more in the subdomain are abstracted in the form of VT-link and VT-link. VT-link and VT-link constitute a substitution for original links, and unique logical topologies are perceived from the perspectives of different cloud applications. Here, for example, seen from Cloud A, VT-link from A to D includes two paths of segment least, A to D directly or A to D through a relay C. But this port is observed with only single segment least by Cloud B. Resources like bandwidth are also distributed, respectively, for different virtual links. A typical instance is the VD-link here from A to B. VD-link for Cloud A is allocated with bandwidth of 5G, but for Cloud B, it is only 3G. As shown below, logical topology may present identically for different clouds and applications. However, resources are reserved exclusively. Next slide, please. In particular, to define VD-link and VT-link, VD-link is a virtual version of a physical direct link which can be identified by local and remote node descriptors, interface addresses, and other parameters of capabilities. Similarly, VT-link represents a virtual tunnel. Taking segment routing over IPv6 as an example, typical attributes include logic ID, node descriptors, maximum reservable link bandwidth, binding speed, etc. To facilitate path calculation and routing in cloud, a new logic ID is defined here to identify a VD-link or VT-link. The logic ID should be globally unique in the network domain as a key. Moreover, in order to meet the customized requirements from different cloud applications at the same time, the bearer network needs to reserve link resources in layer 2 or topology resources in layer 3. Maximum reservable link bandwidth, for instance, is the maximum of the physical link bandwidth reserved for virtual links. When multiple clients share identical physical link, the network controller must reduce the maximum reservable link bandwidth allocated to every one of them except the severity of the original physical link in advance. Thus, the traffic can be preserved from potential and possible interference attributed to other clients. And after the abstraction, the information is written into a database with a key value scheme, and a standard schema template is applied for translation and description. With subscription of specific entities, and then the cloud controller is able to accumulate the knowledge of the running abilities of the network and to further rearrange and orchestrate the path to steer the traffic. Next slide, please. Compared to auto, which is known as application layer traffic optimization, the similarities and differences are listed below. Well, and to be honest, the abstraction of network capabilities is designed to be more explicit and diversified, which leads to the basic conditions of high granularity services. And in auto, we have specific auto service, while in DB-ONAS, a distributed database serves as the server. DB-ONAS also shares identical features and advantages with auto, including extensibility and standardized API. Differently, auto provides a universal and normal scheme for the exposure of network capabilities. And our sites and perceptions within DB-ONAS, we focus on the role of the network controller and the specific cost calculation orchestrator to facilitate network services occupation, which cooperates well with a future condition of the convergence of the cloud and the network. Next slide, please. For further considerations, it is easy to expand more open services beyond the language source services described in this presentation, such as topology, security, and deterministic queues, which makes the framework of DB-ONAS be capable of satisfying future requirements, appearing with the change of the convergence of the cloud and the network. And in conclusion, more perceptions and drafts are expected in the future. We are looking forward to promoting and to cooperating with working groups and as colleagues who have resonated with the issue. Safety and service affinity issues should also be considered in the future. And that's all about today's presentation. Thank you all.
Questions? Anyone on the queue?
Yes, hello. Sabine from Nokia. Thanks for your presentation. Very interesting. So definitely, to mention, I am contributing to the Alto working group. So definitely, we do not take the same approach. You try to steer traffic at the network layer, while we at the Alto working group we try to provide guidance for the application. So it's an off-path approach to really direct the traffic. I would invite you to look at the Alto work that is ongoing, where there are proposals to extend the protocol to integrate compute information. Thanks.
Yeah, thanks. Actually, I've learned some information about auto. I know the concept of auto. That's this is the kind of application protocol for just make endpoint selection to guide the traffic about still make the network domain as a black box. But here, maybe we want to expose some capabilities of the network and to do some traffic redirection work.
Okay. Anyone else? Okay, so thank you, Dongyu. And this, I guess, concludes the session. So thank you very much and see you in Yokohama. So this one, which I was supposed to, okay.